So lines that intersect or meet at a point. And the perpendicular bisectors of a triangle intersect at a point equidistant from the vertices of the triangle. So if the vertices represented, like I said, this is a sports complex, the vertices represent soccer field, basketball field, volleyball field, that place where all the perpendicular bisectors intersect would be the central location equidistant from each of those fields. Okay, so maybe we're at the snack bar. All right. So there it is. There's the special point. That's the point we constructed right there at P. And let's do a couple applications of this. It says the perpendicular bisectors of triangle ABC meet at D. Meet at D. So this is equidistant from each of these. So these are equal distance here to here, even if it doesn't quite look like it. But if that's truly the intersection of the perpendicular bisectors, it doesn't quite look like it to me. Then each of those red segments I drew in are equal in length, okay, according to the theorem. I know, it doesn't look like it. So what that does is that creates some right triangles in here. I'll show you one. This guy right here is a right triangle. It's got a right angle right here. I know that, even though it doesn't quite look like it, because that's a perpendicular bisector. And not only does it hit at a right angle, but it's going to split this 24 in half, making this 12 right here, as well as this. This would be 12 as well. And so I could find, asking us for BC, okay. So I could find BC. BC is actually going to be the same length as BD. Okay, BC will equal BD. Remember, we said all those are equal. So maybe I can draw the triangle over here. So over here, we got a right angle here. That's 5. That's 12. How could I find DC using something we've seen a lot in geometry? It's like the most common. Yeah.
Can't use the Pythagorean theorem.
Yeah, there it is again. Pythagoras is back. So we have DC equals. Set it up for me.
DC equals 12 squared.
Yes. Hey, and this is actually a Pythagorean triple. I know. This thing's now not being this sensitive and stuff. I don't know why. I haven't changed anything yet. 12 squared plus 5 squared. I made my mark for the two. Is it sure? What's up?
Maybe you can check calibrate.
Well, we don't calibrate these, but there is on settings a way to change the sensitivity. I hesitate to make it more sensitive, but then it's like even if you brush like right here, it'll make a. We'll see. So 12 squared plus 5 squared. There's a number that always goes with those. It's always the hypotenuse. It's called the Pythagorean triple. Did you ever hear about those in the past? There's like a 3, 4, 5 always go together, where 3 is a leg, 4 is a leg, and 5 is a hypotenuse. This is another one, 5, 12, and 13. They always go together. So if you see a 5 leg and a 12 leg in a right triangle, it's always going to be 13. You can skip all the arithmetic. Or if you see a 13 hypotenuse and a 5 leg, you know that the other leg will be 12. Always. They've known that for thousands of years. They've used it for resurveying the land. As a matter of fact, they did that in Egypt when the Nile was flooded. They used it to resurvey the land. That was even before Pythagoras came around. They were using those Pythagorean triples. But Pythagoras is one for whom they named. But 144 plus 25 is 169. Square root of 169 is 13. So that's my length. So yeah, 5, 12, 13. If you, it's kind of a little trick for taking SATs, ACTs, is to know some of your Pythagorean triples. It'll save you a lot of time. But there's the 3, 4, 5. There's the, you can double or triple that. 6, 8, 10 is a common one. It's just the doubling of that. You could triple it as well. Not as common. 5, 12, 13. another Pythagorean triple. Another one that's not as common, but still I see it on any kind of standardized testing, 7, 24, 25. So it's like if you know you have a right triangle and you have 2 out of 3 of each side, you can fill in the blank for the other one. What makes it a triple is the fact that the sum of the squares of the 2 smaller ones equals the square root of this one. So if you take, for example, 7 squared plus 24 squared, it will equal 25 squared. That's what makes it a triple. So it's a right triangle in which the 2 legs squared equals the hypotenuse squared. That's actually how you determine that you have a right triangle. That's how they use it in surveying. If you have 3 lengths, right, 7, 24, and 25, and you put them together so that the 25 is the hypotenuse connecting the ends of the other 2 legs, you're guaranteed to have a right angle between the 7 and the 24. It's guaranteed. So that would be a way to square off the land wherever you're resurveying. Been around for even longer than I've been around. So this is the construction that we did. Okay, so flip over that construction. I kind of wanted to get started on those because I know they take a long time. So we did the construction. You guys flip over. Okay, so if it didn't turn out, let's do it again. Okay, we'll do it, kind of go through it. If we're doing it a second time, we'll go through it kind of a little quicker, but let's do it again. I want to have it up here so we can see it. I don't know if it'll turn out as well as it did for me the other time, but it kind of turned out like the best it has for me. So you go ahead and draw a triangle. Yeah, that's fine. Draw a triangle here. And it could be any size triangle. My ruler's a little harder to use. No, that one isn't good. Okay, so here's what we'll do. Oh, there's too much. All right, so here's what we're going to do. We're going to take this guy, and we're going to do a perpendicular bisector of this side. Remember, stretch it out to over half the length. And we're going to swing an arc down here, swing an arc up here, and then go to the other side and do the same thing again. Place the compass point on the end there, and swing an arc down here, another one up here, and then we connect those 2. So there is one perpendicular bisector. And what we discovered the other day is that we really didn't need to do a perpendicular bisector of all 3 sides. We could just do one more of them. Swing an arc above and below. And then from the other side, swing arc so that it intersects those 2 and then connect the 2 intersecting. Is it not working? Okay. What's wrong with it? It might go. So it doesn't lock out. Sometimes if it's not locking out, I notice you can like press your finger on the red piece underneath, and if you can like try and tighten it, it seems to if it has like a threaded part or something, but it'll just. What's that? Pretty sure one. Oh, they are glued. Yeah. Okay. I'm able to bend. Oh, that just shot. A little bit. No, actually, they're glued. It looks like one fits into the other. I don't know if they're like. They may be shot. All right, so let's go ahead and do another one. So you guys got that one, and we'll go over here. Do another one. I'm gonna make this a little shorter. Swing an arc here, an arc over here. So I'm swinging an arc to the left and to the right of this guy, and then the other side. Swing an arc. Swing the arc in the right spot. So I have to go back. Or I changed it. Change itself to it. That's good. So we got this guy right here. Oh, it's not quite halfway, that's why. Reset. Some like icons. So, oops, don't paste. Sorry, one of my videos, I just pasted on the video links. Okay. So if that happens and they don't quite meet, you just stretch it out a little farther. And try swinging an arc again. Then go to the other side. Do the same thing from the other side. Swing an arc here. Swing an arc there. And take your straight edge. Connect to. This one's intersecting almost outside of the triangle. They'd be doing an obtuse triangle on this. If you had one angle bigger than 90. I think the obtuse, I think it's outside of the triangles where they meet, which is fine. That's a possibility. So then what you do, this is the last part, this is the part we rushed at. If you place your compass point where the two of them intersect, that's the circumcenter, stretch your compass out to this point as best you can. And then just go ahead and swing an arc. So we're measuring this distance from here to any one of the vertices. And then swing an arc, and it should hit. Because that one's not as good, but just make the dot bigger here. Yeah. Perfect. So it should hit each of the three vertices. So that's the circumscribed circle. It goes around the triangle. So here's the center of the sports arena problem. All right. So we're going to do the same thing with the angle bisectors. Okay, so the angle bisectors in a triangle intersect at a point equidistant from the sides of the triangle. So say the sides of the triangle represented paths or trails or roads, then this would be the center. So this is the race course, and this is the medical center there. So you can go from the road and make a path from there to get people to medical center here. But this point is called the in-center of the inscribed triangle. So here's what's special about that quick little application. It says GE is equal to 2x minus 7. So GE is this guy right here. That's 2x minus 7. I'm thinking we're going to set some things equal maybe. And then GF is x plus 4. So GF right here is x plus 4. According to this theorem, these distances here, here, and here are all equal. So if I want to find GB, it's going to be the same length as either of these two that they've given me algebraic expressions for. So it's like when in doubt, what do you do with the algebraic expressions? Yeah, when in doubt, set them equal. I mean, it could be that they add up to something, but in this case, that's not it. It seems like more often than not, it's set them equal, right? So set them equals 2x minus 7 equals x plus 4. Subtract the x over. So x minus 7 equals 4, and then add the 7 over. we got x equals 11. Add the 7 over to the 4, that x equals 11. So the length of GD is going to be whatever the lengths of those other two is. So you just plug it in. So 22 minus 7 is 15, or 11 plus 4 is 15. If you just plug in the 11 for one of these, either here or here, you get 15. So GD is equal to 15. So some of your homework is just setting up and solving an algebraic equation based on the fact that either the lengths from the center to the vertices are equal, or the length from the center to the sides are equal. And whenever we go from the end center to the side, you have to go at a right angle. It wouldn't make sense just to hit it randomly somewhere along here. You've got to go the shortest distance from the end center to the side, which is going to be a perpendicular. It's not the perpendicular bisector, but it is perpendicular. You hit it at the right angle. Otherwise, you're kind of arbitrarily deciding the path that you're going to take. You can't do that. So let's do that construction. So draw a triangle, whatever triangle you like. Make it about, you know, I think I give you a whole page on it. So go ahead and do that. So draw a triangle. Actually, this one you got to fit the circle inside of it, so maybe you keep that in mind. It's kind of nice if the triangle is not too small. You got to get a whole circle inside of it. It'll turn out better for me. A little bit better. All right, so now this time, what are we doing this time? You remember which construction it was in this theory? That was the first one. You remember the other? The what? Angle, yeah, it's the angle bisector. The parallel kind of is related to the angle bisector, but the parallel was the one we used to get corresponding angles of the congruence. So there's two constructions you should know how to do. It's perpendicular bisector and then the angle bisector. So we're going to do the angle bisector. And we've learned from our previous one that we only need to do this twice. Right? So we're going to do an angle bisector off of one of the angles. So go ahead and swing an arc through the angle. And then from the place where the arc hits the two sides of that angle, we're going to swing two more arcs. And they'll just be somewhere in the interior here. So swing an arc there. See where my compass point is? Let me do that. So an original arc through the angle, and then where the arc hits the two sides of the angle, you're going to swing an arc from one end, and then from the other. One end and then from the other. And you'll know you have the angle bisector because it'll look like it splits the angle in half. And then draw this guy. So there's one of my angle bisectors. It looks pretty good. Looks like it splits that angle in half. So that's one of them. So from the ends of this, swinging an arc there and there, and where they cross, connect that to the vertex, and you got it. So I'm going to do another angle bisector off of this bottom angle here. And it's your choice. You can choose whatever angle you want. I'm even going to keep it the same length. And what's cool about this angle bisector, you can usually keep it the same and go again from here so they don't overlap. And they're pretty close. But I might want to stretch it out a little bit. There we go. So I'll do an arc up here. It's okay to change the length. No, to get a couple arcs in there. But you could stretch it out before you do those second intersecting arcs. The main thing is that you're getting a distance equidistant from each side of the angle. This way. Okay. That's so close. All right, see how this looks. Okay, so where those two intersect, I'll put a big red dot there. Should be the end center. This one doesn't always turn out quite as well. If you want to be really technical here, if you really want to make sure that you get that circle so it's really truly tangent to each side, here's what you have to do. You got to go ahead and do, you remember the smiley face, perpendicular bisector line. Here's what you have to do with that. I'll do it in red. Some of you might be able to eyeball it and get it. Like you can take this, you can kind of do the cheater way. Take this guy and stretch it out and eyeball where you think perpendicular to this base would be, and you will probably be okay. But I'll see like a lot of circles that are kind of tangent to the sides, but not quite because you've eyeballed it. But if you really technically want to do this construction correctly, here's what you got to do. You got to do the smiley face guy, and then it goes like this. So smiley face goes like that. You swing an arc. There's our smiley face. From that point where the two intersected, you swing a smiley face. So go ahead and do that now. And then from where the smiley face hits the sides of the triangle, we're going to swing two arcs down below. So I'm going to take this guy, move it right here, maybe stretch this out a bit. I'm going to swing an arc here, and another one from the other side. Swing an arc there and there. So there's my smiley face construction used back in chapter 3. Of course, I could have probably done this too with my, basically I have a protractor ruler, right? But you don't. So, right there. And draw in perpendicular, and that's the length you want to use. That may even be off a little bit. It's not coming from the center of the point, but this is the length you want to use for the radius of your inscribed circle. Okay, but it's got to be perpendicular to this, and you could probably eyeball it. It'd be pretty accurate. But shorten this guy out. My dot's so big, I don't know how accurate this will be, but so I'm going to keep shortening this up so I've got it. That's pretty good right there. But that's about what my circle radius should be. I think it looks, I got some human hair going on in here. So great. There it is. Change to blue. And let's see what happens here. Yeah, you can see I have some human hair. I went off a little bit over here. Hope yours turned out better, but that's the idea. So theoretically, if my point hadn't been so big, making that point that big kind of messes it up. You can even see where my perpendicular hit that point is like off on the left side of the point. So right there, it's off. And then it gets exacerbated as you go around, and it's more and more off. Although right here it's good. It gets off here, and then it's off here as well. So that's it. Circumscribed or inscribed circle. Anybody need any help with that guy? You might have people next to you to help you with it too. Yours looks good. It's at least as big as mine. Yours is pretty good too. It's supposed to, that's the idea. But look, yeah, mine's on too. Mine's like outside, you know, all the way through or whatever. What's that? Yeah. Good idea. All right. That's it. So next time, oh, it's medians. That's what it was. The centroid is the intersection of medians. It's like a balance point of the triangle. Here, to take a triangle, put it on cardstock, cut it out. Here, if we really constructed it carefully, the intersection of medians would be the centroid or the balance point of the triangle. Doing an orthocenter, I don't know what the application of that one is, but that's the intersection of the altitude. That'll bring a smiley face back. You can collect all that homework. Is there any homework? First chair is take care of it. Okay. Any other questions? You can grab a book or you can grab a Chromebook and